Welcome to this IAP colloquium. It's my privilege to introduce today's speaker, Fabio Acero. So Fabio is an expert, is a well-known expert in the modeling of cosmic ray and particle accelerators in our galaxy and in their observations through the X-ray and gamma ray domains. So he's a member as well of the Fermi, CTA, and Athena collaborations, right? Fabio obtained his PhD in 2008, and then he moved to Montpellier for a few years as a postdoc, where he joined for some time the HES collaboration. Then he moved on to a postdoc at NASA as a NASA postdoctoral fellow. And then he stayed there for 2 years, and then he joined AIM, where he's been now ever since at Acero. And so today he will be talking about galactic particle accelerators as viewed in the X-ray and gamma ray. So thank you again, Fabio, for being here.
Thank you, Martin, for the introduction. Can you hear me okay? Yeah, I think this is working. So thanks a lot for the invitation. It's my honor to be here and to tell you about all those interesting objects and about high energy astronomy, cosmic rays, particle accelerations, and show you lots of, I hope, nice images of those beautiful objects that are the supernova remnants. So this will be a kind of a mix of several topics in this presentation about particle acceleration mostly, but also about what we know and how we can probe explosions of stars through the supernova remnants. So like all cosmic ray talks, usually we start with this, Victor Hess, spectrum, blah, blah, blah. I will try to make something a bit more original with a project that we have that is so we have been organizing a series of symposium at the Institut Pascal on Paris Saclay, and we do some outreach. And one of the outreach event that we were doing is to try to make une bande dessinée about astroparticle. And so we received a month ago the first set of 15 pages, and the introduction starts with Hess. So I will just do this one slide in French, as everything is in French there. And so, as you know, the history. Donc, Victor Hess a fait des vols en ballon pour mesurer les rayons cosmiques, le rayonnement. Et la question à l'époque était qu'on avait un taux d'ionisation, il n'y avait pas d'histoire de rayons cosmiques, et faire des mesures pour dire ça peut venir du sol, de la radioactivité des roches. Et donc, on va faire des vols en ballon pour pouvoir voir que normalement, quand on s'éloigne, le taux devrait diminuer parce que ça vient du sol. Et donc, c'est ce qu'a fait Victor Hess avec différents instruments et de voir dans des vols en ballon en montant de plus en plus haut que normalement, ça devrait diminuer. Mais lors de son vol de plus haute altitude, le 12 août 1912, il était confronté à le fait que dans ces mesures, ça diminuait un tout petit peu lorsqu'il descendait, lorsqu'il montait à 1 km, mais après 1 km, le nombre de réactions ici remontait. Et c'était ça qui était donc incompréhensible, d'essayer de comprendre. Il devait y avoir, et donc lors après de son discours de prix Nobel, il disait qu'il pouvait y avoir peut-être un messager de l'espace ou des rayons cosmiques, le terme est venu après. Mais voilà, donc c'est une bande dessinée qu'on est en train de travailler qui s'appelle Les messagers de l'espace, ce qui va présenter l'astroparticule, les rayons cosmiques et les différents outils, par exemple les CTA ou les neutrinos ou les choses comme ça, autour de ces thématiques-là. Voilà, donc now that we have this more original introduction, I will go back to this. So this was measured a century ago by Victor Hess, started, and so we still have this puzzle or where they are coming from. And so just what you have to know, is there a pointer? I think I saw one. So what you have to know here, most important thing is that the spectrum of cosmic ray is a power law like this with a few deviation, and the one that we are more interested in here is that we usually divide this into 3 blocks, and that the cosmic rays in this energy range are thought to be mostly accelerated locally in the galaxy. And so this is the same spectrum here, but multiplied by another factor here, and that there is this knee structure here. So those are the cosmic rays that we measure at Earth, and you see a change of slope. And we think that those are mostly galactic, and that more or less this knee, it is called the knee of the cosmic rays here, should be around those energies. So 1 PeV is 10 to the 15 eV. So we're talking really about highly energetic particles. And so it's been a long debated subject. What are the sources in the galaxy that are accelerating the bulk of this? For highest energy, more particles like Auger particles, they are thought to be extragalactic and, for example, AGNs or something like that. So in the galaxy, the usual suspects that are explored are the following ones, and they are somehow all related to the stellar graveyard. And so they are objects that follow and that are related to the end of the life of massive stars or degenerated white dwarfs. And so, for example, supernova remnants. So supernova remnant is what you have centuries after the explosion of a supernova. And this is typically what you see in X-rays. And the acceleration is, I will go more in detail later, but the blue rim that you see here is the forward shock, the front shock, and we're talking about a shock that goes at 5,000 kilometers per second, and that can generate some turbulence and accelerate particles. The energy power from the source is the kinetic energy of the explosion, and you can have acceleration at really high energies for a few thousand years after the explosion. Then we have other accelerators that are the pulsar wind nebula. So this is the famous picture of the Crab Nebula. You have a pulsar here that is making a wind of you have a relativistic shock and you have a wind of electrons and positrons. And here the energy power is the pulsar rotation, the slowdown of the pulsar rotation. And those can be seen much longer timescales after the explosion. The Crab is young, but we see other pulsar wind nebulas that are more than 10 kilo-years old and that still accelerate particles. Then we have the pulsars themselves. So also there is a zoom in scale. So this is like 5 parsec, 10 parsecs. This is smaller, and this is 10 kilometers here, the pulsar there. And so you also have acceleration in where exactly is the acceleration happening. There are different theories, but in the polar gap, the slot gap, in different, those are the lines of magnetic field here in blue. And so the power this time that is powering the engine is the electric field generated by the pulsar rotations. And those can be seen really at a much longer timescales. Then in this after death timescale, you have objects that are even on a longer timescale accelerating particles. They are called sometimes the zombie pulsars because there were pulsars that have been slowed down, very old, and sometimes they have a companion, and the companion, you have accreting material that we respin by momentum transfer, respin the pulsar, then to milliseconds. The Crab is 50, 60 milliseconds, and then those can be seen mega years after the explosion. So those are very old objects. So what I will mostly focus on are supernova remnants in P-wind. So usually if you have a core collapse massive star, you have the supernova remnant that is outside. You can have or not a P-wind and a pulsar at the center. And for those objects, mostly for the cosmic rays, we want to answer 3 questions in order to find the sources that are responsible for this acceleration. We want those objects to be able to accelerate the particles that we see on the cosmic ray spectrum, that is electrons, positrons, protons, and heavier ions. So those objects need to be able to accelerate this composition. Then they need to be able to have enough energetics to accelerate the flux. Those need to be able to accelerate in sufficient numbers the cosmic rays so as we see them at Earth. Of course, there are some transport effect also. And then mostly also, as I said, they need to reach this near of cosmic rays up to the highest energy. So in this global idea, those are galactic accelerators. So supernova remnants also, supernova, they inject kinetic energies. That's something that is useful also for the feedback of galaxy in the simulation. If you have or you don't have the supernova feedback, as a kinetic energy, this changes a lot the properties in the galactic ecosystem. So they really play this role of injecting kinetic energy. They are, of course, creating the nucleosynthesis of all the heavier ions. the accelerated particles, as I said. And so what I'm interested in is that you have this loop between the explosion mechanism. We don't know exactly how they explode, but centuries later, if you look at the supernova remnant, you have some fingerprints of, for example, the instabilities, the asymmetries in the supernova explosion that are still visible in the supernova remnant. And in some cases, you can have a pulsar wind nebula. Here is another example. And we try to understand, for example, some pulsars have wind, some do not, some have magnetars, buried magnetic field, higher magnetic field, what was the progenitor, etc. So by studying the remnants, you can have some clues about the explosion process for core collapse and also for type 1As. And so what we do as a community, or what I do, is to try to look at those objects with various observatories, mostly in the high energy, so X-rays, GeV gamma rays with the Fermi-Lat space telescope, or on the ground with the Cherenkov telescope. So some words on those supernova remnants. Something that I like about those historical galactic supernova remnants is that it's one of the few rare examples in which we can use 1,000 years old astronomical records. It's true also for the solar spots, for the solar cycles, which you have records. But it's less true for AGNs. You cannot use Chinese records to study AGNs or GRBs. And so in the last millennia, we had 5 galactic supernova. SN87A was in the LMC, so not really galactic, nearby, but not galactic. And it was visible at that time, very bright in the sky. I will show some examples. And so it was recorded by a lot of astronomers around the world. And we have current models say that we should have more or less 2 supernova, type 1A or core collapse in the galaxy per century. And you can see that those are small number events. So of course, but they happen in group, and then there are big gaps. And this is what you expect for Poisson distribution, but we are unlucky that we haven't seen one in the last 400 years. So now looking at remnants, we know that they are younger. There is one example in the galactic center that we think is 150 years old, just that it was very far away, 8 kiloparsec, and the optical extinction made it impossible to see by eye. And I will focus on one example, Tycho. So Tycho SN 1572, that is named mostly about Tycho Brahe. And so a year and a half ago, I organized a special session on this at EAS to celebrate the 450 years of Tycho supernova. And so it was seen in Europe starting November 1572. At that time, it was brighter than Jupiter when it was observed in the first week. And this is here, Nova Stella. So of course, at the time, there was no knowledge about supernova, etc. It was discussed whether it was in an atmospheric event, whether it was a star, but it was not moving like the planet, so it was not a planet. And an interesting note is that, so it was 1572, the book of Tycho Brahe about this one, De Nova Stella, was in fact published in 1602 after Brahe died. And mostly Kepler was finished and edited by Kepler. And Kepler had the luck to see 1604, that is now named Kepler supernova. So in a way, Kepler has published 2 books on supernova. So that's a really low H index by today's standard, but he's probably the only astronomer to have 2 publications on galactic supernova. And yeah, so during that time, there were some people that witnessed those 2 supernova, and now in the last 400 years, nothing. So that's bad luck. And just an example also that, of course, not only Tycho Brahe witnessed those events, it was witnessed all around the world. And for example, here, some books also that were written about it, but now we from a European point of view, we have recorded mostly Tycho Brahe, but there were several books, not only the one Tycho Brahe Kepler. And from Al-Mutahar here, and so there appeared a star here in the path of Ursa Minor, and it was larger than Venus. Of course, at that time, they were saying larger, meaning brighter, but when something is very bright, you have the impression that it's really the disk of the star is larger. So I think they were meaning larger, thinking that the angular size were larger, but it's an optical effect that brighter things appear bigger on the eye. And also, like all those astronomical events, it was true also for the Chinese astronomer that something that appears on the sky that was not there before is a bad sign. And that this appearance on the sky probably indicates the death of some mighty king or great leader in that region. And that it was true also for Chinese astronomer that the sky was divided in quadrants. And if there was a comet or a nova or a supernova happening in one quadrant, each quadrant had an equivalent in China in one district. So if something happened in this region, means that something bad would happen in this specific region. So it was like, of course, at that moment, astrology and astronomy were kind of related. So now going back more to the supernova remnant thing. So here is a slice of the different parts that I will mention, and just to give you a schematic view of what I will mention. So you have the supernova that is injecting about 10 to the 51 erg kinetic energy in one spot. This will create a shock wave. This shock wave here will expand. In the early days, we're talking about maybe 20, 30,000 kilometers per second. Then after it's slowing down, and centuries after, we have typically 5,000 kilometers per second shock wave propagating. Then along with this shock wave will shock the interstellar medium, which is shown here in blue. Then you have a reverse shock that is going inside that will shock the outer layers of the star, what we call the ejecta. And the particle acceleration here will happen here in this region, going back and forth and accelerating particles. So this is to show you that you see some instabilities here and sometimes some asymmetry that can be a trace of if there were some asymmetry in the original explosion. And so what kind of physics can we do with supernova remnants? So as I will mention later on, we can accelerate particles, we can hit, for example, and probe also the surrounding medium. And there is a lot of collisionless shock physics that can be probed and understood in those shock. And in the shocked ejecta here in yellow, this studying those ejecta gives you some information about the supernova type, whether it was a core collapse or a type 1A. It gives you some indication about the progenitor system. And you can also, as I will show you, kind of reconstruct the 3D distribution of those ejecta that will inform you about the explosion mechanisms. And so for this, I will just show one slide of more methodologies here, and it has a link with CMB, Planck, etc. So I think that's a good audience here, is that we have been working with some people that worked on the CMB and the Planck data at CEA Saclay, in which they have developed a component analysis method. So a little bit in Planck, I think there was some independent ECA, independent component analysis. And this is the same kind of family of methods in which you want to do a decomposition in which in Planck or in X-rays we have data cubes as well. You have a data cube here that is Ra, Dec, frequency or energy. And you want to separate that to a linear combination of a spectrum and an image plus a spectrum and an image. In the case of Planck, what you want is to recover the image of the CMB, the image of the dust or the synchrotron, etc. And this method here is a blind source method in which you want to estimate the AI and SI component here without any prior information. If you can do it semi-blindly, for example, in the CMB, you know the CMB spectrum and you know that it's the spectrum all over the sky. But in X-rays, we don't know. You can have that method purely in blind mode. And so we use that method, as I will show on the next slide, to recover some of the ejecta components. And the idea here is that you have no prior information, but you want each component to be sparse in the wavelet domain. So you want some components that they don't have the same morphological signature and spectral signature in the wavelet domain, and that will help you to separate them. In the CMB case, we know that the morphology of the CMB is not the same as the morphology here, and their power in the wavelet space is not distributed equally. And so this is what we used here, this kind of same method initially developed for the CMB to be used for the X-ray data cube. So in X-ray, we have also a data cube. Here you should have different slices. This is Tycho supernova remnant 450 years after the explosion, as seen in X-rays. And for example, in X-rays, you have emission lines. So you have the continuum, then the emission line from the silicon, the sulfur, the argon, etc. And so here is a zoom on the silicon line. And if you take this data cube, you use the method, and without any information about the instrument's response, the redshift or whatever, the method was able to separate that the black line, the observed spectrum, can be decomposed into a continuum. Here, that is the synchrotron emission, then a redshifted emission line, the silicon emission line, and a blue shifted emission line. And here you have the corresponding images. And so this was really helpful in order to separate the foreground from the background of the shell in order to reconstruct this map. So using the background and the foreground, we were able to reconstruct this map that is basically the velocity, the redshift map from the average redshift map that is telling you that, for example, something red here, it means that along the line of sight, the ejecta is predominantly coming red away from you. And this gives you a 3D view of the distribution of the ejecta. And what you see is that it's not a sphere. If the explosion was perfectly spherical, everything will be white because the average along the line of sight will equilibrate. And so this is telling you about the clumpiness of the distribution of the ejecta, and also that towards the north, it was blue shifted and here. And so probably the explosion was oblong shape in that direction. And also with another method, my PhD student, Leila Godino, was able to map. So in X-rays, we have observation of this every 3 years or 4 years. So you have a movie and you can see really the shell expanding. And if you compare two different epochs, you can construct this velocity map vector here. And you can see, for example, blue means faster than 7,000 kilometers per second, that there are some dense ejecta here that are ejected at a faster speed in the plane of the sky. And so this is also telling you something about the asymmetry of the explosion in this, and this is a type 1a supernova here. And also what we can do, this is a spectrum, for example, an X-ray spectrum taken from one small region, one small patch of the sky. And so here are the different lines that I was telling you about. And from this, you can construct a map of the abundance ratio. So for each region of the sky, you can say the composition in heavy elements, the ratio of magnesium, silicon, calcium, silicon, etc. And you can construct a map of it. And then you can take this and you can see that it's not homogeneous. So for example, magnesium was mostly ejected in one direction. So the explosion mechanism that was here is not spherical. And we compare this with type 1a explosion models. So the idea of the type 1a is that you have a white dwarf that is accreting material, and there will be a hot spot in which there will be a thermonuclear reaction that will make a deflagration flame, and that will consume the white dwarf. But there, in the models, you can have 1 ignition point, 10 ignition point, and so those are not known in the models. And you can see that different models with different ignition points will predict different nucleosynthesis yields. So this is the ratio of sulfur over silicon, magnesium over silicon, etc. And so and the histogram here is the histogram of the map that I showed you before, the data, and those are the models. So there is not a perfect match, but it seems to say that a high number of ignition points here, like the red line, is not favored by the data when you look at the nucleosynthesis. So in this specific type 1a, maybe the number of ignition points is low. And this, you have two different channels for type 1a, single degenerate or double degenerate. And so this will give indication on those scenarios. So now moving more to the other part of the talk that will be more about particle acceleration. So in particle acceleration, in the shock here, you can accelerate particles when you have this shock. The shock is moving. The charged particle will create a turbulent field line here. And on the turbulent magnetic field, the particle will bounce back and forth. And every time they cross the shock, they will gain a small amount of energy, but they will go in that cycle many times, and they will gain energy like this. Here is a numerical simulation in which you will see the density, the magnetic field. You start from a random magnetic field, and then you will see particles that will go through the shock, and the color of the particle is the energy. And so, for example, the shock is developing. You have the particles here that are bounced back on the shock. They are all blue, and at some point they will change color. You can see that the magnetic field is self-generated here. And then here they are trapped, and some of them go back, change color, and with time we'll gain some energies here. So this is an illustration of the path of the particle. They go, they enter, they come back. And what is interesting here is that this magnetic field turbulence was not existing at the beginning. The particles, they are charged particles, they generated their own turbulence to bounce back and forth. So you have particle accelerated in the shock, then those particles, they are charged, they will not travel in straight line in the galaxy. So what you see on the cosmic ray spectrum is not coming from this direction. They are moved around in the galactic field. And so what we do is to try to study cosmic rays in situ in the supernova remnant. For example, charge accelerated electrons will produce synchrotron radiation. They will also produce inverse Compton radiation that you see in gamma, and they will also produce gamma ray when charged protons accelerated protons interact with matter. And so this is a picture of one of those supernova remnants seen in X-rays, mostly dominated by electrons, synchrotron radiation in X-rays. Then here in gamma rays, you have a mix of inverse Compton and pi zero decay. And this is in TeV gamma rays seen with the Cherenkov telescope here for that same object. And then I will mention about a recent instrument that was built in China that really looks at the highest energies. So what we do usually is that we look at those SED, energy, flux energy as a function of energy. In X-rays, you have the synchrotron. Then at those energies, you want to probe whether you're dominated by the leptonic electron inverse Compton or pi zero decay to know what are the particles that are accelerated there, what is their maximum energy, and what is the flux. And so the idea was that young remnants they have the highest shock speed, like Tycho, for example. They have a lot of kinetic energy, and so they should be able to accelerate particles to very high energy. The faster the shock, the higher the maximum energy that the acceleration process can bring you to. And so historical young remnants like Cassiopeia A or Tycho would have been the ideal candidates. But if you look at gamma ray observation, so this is Fermi, and then you look at the spectrum, and we want to remember to have PeV energies for the particles. So this should be up to hundreds of TeV in here. You can see directly here that those spectrum, they fall down. And like this one, this spectrum falls down here. And what we would have hoped would be that this continue as a straight line and that the break happens here. And this is not the case. And so the spectral index of the accelerated particle should have been, the theory predicts something around 2.0, 2.1. And what we observe is something much steeper, and even much steeper in that case. And so for some reason, those young remnants are not the pevatrons, the one accelerating to very high energies. And reasons can be diverse for those kind of objects. And a zoom also on Kepler. This is a work that we have been doing 2 years ago. And it was Kepler is one of those historical supernova remnants. It's the most distant of those historical objects. So it's the faintest one. And that's why it needed really deep observation time with Fermi and with TeV gamma rays to observe. You can notice how bad those images are in TeV when compared to the beautiful images that I showed you at the beginning. This is in green here what they looked in X-rays, and this is in gamma rays. You basically just have a big blob because the PSF in gamma rays is not as good as in X-rays. And so for this object also, we have the same issue basically. If you look at here, we would have expected the spectrum to extend up to the very high energies, and we see a drop in those different cases here. But what we think is that they might still accelerate particles to a very high energy, but not on the totality of the sphere, just maybe on some spots, and you need higher density to reveal those accelerated particles. And currently, with the resolution that we have like this, you cannot make a map of whether the spot is coming from here, here, or here. So definitely, we don't have the spatial resolution to disentangle those components. And that brings me to the Cherenkov Telescope Array. So this is an internal collaboration to build a ground Cherenkov telescope. So I will mention what this is. And the idea is that, so gamma rays, TeV gamma rays are the highest. After gamma ray, there is nothing. That's the highest range of photons, the highest energies. And to stop them, you cannot use a mirror. You cannot use anything. The gamma ray, they go straight to the mirrors. And so to stop them and measure their energy and deposition, usually you need a converter, so something dense that will stop it, like a particle physics experiment that will convert it into pairs of electron and positron, and you will measure that. The problem is that at TeV, you cannot, it's hard to find, to construct and build something in space that is heavy enough to stop those. And so what we use is the largest converter that we have around, that is the Earth's atmosphere. And so here you have a gamma ray that arrives that will interact with the atmosphere and make a Cherenkov shower here. So the Cherenkov light is, this idea is that you have, so Cherenkov light is also what you see in nuclear reactor. So the Cherenkov light is produced when a particle moves faster than the speed of light in the medium. So not faster than the speed of light in vacuum, but in the medium, and will create a flash of optical blue light. And here, that's what you have. You have the gamma rays that is creating a cascade of particles. Those particles move faster than the speed of light, and they will do a Cherenkov flash that lasts for about 10 nanoseconds. So you need high-speed cameras in order to record optical blue light at very high speed to see this flash. And if you have a collection of telescopes, this is one blue flash, and that it's hard to give the position. But if you have several telescopes, then you can combine this information to triangulate the position in the sky and to have a better accurate reconstruction. And the more telescopes you have, the better will be your reconstruction here. And this is the goal of the Cherenkov Telescope Array here that is in construction. There will be one site in the north, in the Canary Island. So those are not existing. Those one are the older generation that are already existing. But instead of 2, we will have 13 of different sizes optimized for different energy range. So in the Northern Hemisphere and then in Chile, have a much larger array optimized for a different energy range. And so we've been making simulation of what we expect to see with CTA. And this is a simulation of the galactic plane survey that we could obtain here. And up to now, we know about in the galaxy less than 100 sources. And this survey with CTA will bring this number to more than 500 sources. And the population of sources that we expect to detect are supernova remnant, pulsar-wind nebulae. There are some sources of those 100 that we still don't know after 10 years what they are. You have also some pulsar and some binary systems. And for example, for the supernova remnant with CTA, this is a simulation of the simulated one, those dots. And the ones that have a cross are the ones that we detect in the data challenge. And you can see that we can detect some of them up to 20 kiloparsec, so the other side of the galaxy. So we expect to have, we know about 10 today, and we expect to detect about 30, 40, so bring a total from 10 to about 50 objects, so to have a population of supernova remnants, and to detect some of them up to the other side of the galaxy. And this is the same thing for the pulsar wind nebulae here, where all the blue dots are the simulated one, and the colored dots are the one that we detect. And we should detect all of them all across the entire galaxy. And in terms of completeness, so we will not be 100% complete, but we detect half of the ones that have a high E dot. So those are considered high dot pulsars. And so we should detect a good fraction of them. So as a first conclusion of those cosmic rays, so using X-ray astronomy, you can constrain the environment around those supernova remnants. You can constrain the progenitor, whether it was a type 1a, a core collapse, the nucleosynthesis yields, and then if they accelerate electrons or not. In gamma rays, that's the best way to probe the proton population. Remember, dark cosmic rays are mostly protons, in fact, and electrons is a small fraction of the spectrum of cosmic rays that we see. And in gamma rays, you can probe those populations, but there is a compromise to be found between high shock speed and high target density to create gamma rays. And so about this paradigm of supernova remnant and cosmic rays, yes, then can accelerate electrons, the protons. This has been observed. I didn't mention, but the energy budget of the supernova that we know is compatible with the spectrum that we observed. The one thing that really doesn't work so far is that they do not seem to accelerate particles up to the very highest energies. And 15 years ago, people they were saying, yes, they will accelerate, we will detect them. And now, clearly, this is not the case. So if they cannot, who can? And so really a paradigm shift in the last 3-4 years was that maybe, at least for the electrons, P-WIN, as I will show, a very promising candidate, and this has been a surprise to the community. The other option are super bubbles like the Cygnus cocoon that have shown to have accelerate particles up to incredibly high energy. And for example, this is what has been revealed by LASSO. So LASSO is a Chinese experiment built at 4,000 meters altitude in the plateau in Tibet. And it's an incredible detector that they've built incredibly fast. And I think they started more or less at the same time as CTA, and CTA is still in construction. And they have revealed a map of the sky at above incredibly high energy, above 100 TeV. So there are not a lot of sources, but we're talking about incredibly high energy photons. 10 years ago, people were saying it's not even sure that it's worth building an instrument because there should be 2 sources at those energies. We don't see what sources could be accelerating so high. And in the first catalog, they have revealed, I think, more than 70 sources, and we were thinking there will be 5. And for example, some interesting thing that we're also seeing a little bit with HES before LASSO is that some objects at high energy have an incredibly high spectrum that is going up and up like this, and that have a really hot spectrum. And for example, LASSO has also revealed some sources that are really strange, in which at low energy, this is still high energy, but there is nothing. And then above 25 TeV, you have some sources appearing at the extreme high end. So imagine this kind of particle accelerator that is dark in X-rays and everything else, and in ultra high energy, it's shining, and we still don't know really what they could be. So the open questions in the field here are that, for example, what are the explosion mechanism of supernova? You probably know that type 1a supernova are used as a standard candle in cosmology, but in fact, how they explode, we still don't know. What is the really basic reason? There are several channels, or the single degenerate and double degenerate channel, how it works, what is the nucleosynthesis yield, etc. And so those are things that you can study in the galaxy with the remnant of those supernova. Also for core collapse supernova, there are some predictions. So we saw some neutrinos from 87A, and with the newest generation neutrino, if there was one, we could see it at a further distance. Also probably gravitational wave, but this seems limited to really the nearby environment. And some interesting thing also recently is that if remnants, centuries after the explosion, cannot accelerate particles to very high energy, could supernova in the first months after the explosion, where you have this, remember, this high shock speed that is 20,000 kilometers per second instead of 5, this will be the ideal condition in which you have high density because of the red supergiant wind and very high shock speed. And so this is something that we have been looking at in CTA to see. And this kind of thing have never been seen. We have never seen gamma rays from a supernova in Fermi or at GeV or at TeV energy. So this will be a new class of source. And the physics is a little bit similar, but a little bit different, especially for one thing, is that, so we're talking about this time the supernova that is a week old versus 450 years old. And one thing is that at the beginning, of course, you have the supernova, you have the photosphere that is here, that is supernova, are of course, very bright in optical. So you have lots of optical photons. And there is a process in which you can have gamma-gamma absorption, in which a gamma ray photon interacting with an optical photon will disintegrate and will be absorbed and creating a pair of electron-positron. And so you accelerate particles, you create gamma rays, but at the same time, they are absorbed by optical photons. So the exact amount of gamma ray photon that will exit this process is a time evolution and geometry dependent model. And this is something that we have been working on. And just to give you, so we start from this model, we do the modeling, we do the simulation of the observation, and after several steps, we ended up in something that is very preliminary, but that is this kind of plot. So imagine that you have a type 2p supernova. We had different modeling ways, or a very bright type 2n supernova that is high kinetic energy, higher density. How far could we detect that kind of object in the nearby environment if we invest something that is reasonable, like 40 hours of observation? And you can see that type 2p supernova, those first two, here this is 10 megaparsec, and this is the 3 sigma threshold for detection. You see that it really needs to be nearby objects, so less than 10 megaparsec. The good thing is that in less than 10 megaparsec, there are some galaxies that have a high star formation rate, in which we expect that the core collapse supernova rate is rather high. And type 2n, the good news is that they can be visible up to a very larger distance because they have this higher luminosity and density. So, but we're talking about rare events, and probably this is a few events per decade. So we will not detect a lot of them. And the last word I wanted to mention is about X-ray astronomy. So there is this ESA project. So LISA and Athena are the two future class L mission from ESA. They have been going some turbulences because of budget constraint from the ESA in the last 2 years. And so first, what will Athena do? Athena will be a very large mirror here with 2 different kinds of detectors. One of the camera will be a microcalorimeter. So the microcalorimeter is a new way of measuring the energy of an X-ray photon. It's not a CCD type camera. You really measure the heat deposition in small pixels. And from this heat deposition, you can be much, much precise, have a much better precision than the CCD camera. This is typically a simulated spectrum of what we have with the current XMM ESA X-ray telescope. And with Athena, you will go from this to that kind of spectrum. So look at, this is the iron K iron line complex, and going from one bump to a collection, an incredible collection of small lines in which you will constrain the abundances, the nucleosynthesis, the 3D mechanics much, much better than what you can do today. And so the good news is that in November 2023, the ESA SPC Science Program Committee has approved a new Athena. So now they want to call it New Athena, in which the design has been revised to fit within an envelope of 1.3 billion euros. And they have restarted the industrial activities first quarter of 2024, so now. And the idea is to have a mission adoption in 3 years. And the target launch date is still in 15 years from now. And yeah, and so this is to conclude a simulation that I made about if you look at those objects as 3D objects, when I say 3D, in this case, it's Radek and energy. Having a better spectral resolution means that you can, as we've seen before, resolve the lines with a much better precision. And then you can see those data cubes here. Each slice here is in fact a line. And so you will be able, if there is a red shift, blue shift, then you can see those lines here that will appear in a much better fashion. And we will be able to see really the 3D dynamics of the ejecta with this high resolution spectrometer. And I think, yeah, right on time. Did I have some? No, that's it. Thank you.
Thank you very much, Fabio, for this very clear and exhaustive overview of the field. So do we have questions? Yes.
Thank you for the talk. You mentioned the processes with electron positron, but you didn't mention any type of, baryonic nucleons or protons and so on interactions. Can they be, because they will be, accelerated, the nuclides will be accelerated to very high energies in the shock. And in the SN remnant, and therefore, is there any, hadronic reaction can be responsible for PV emissions? Yes. And also cosmic rays, high energy cosmic rays.
So yeah, at the shock, you will accelerate any charged particles, so electrons, protons, ion, silicon, iron, etc. They will all be accelerated at the shock with different energy depending on the charge. And yes, they are accelerated. We know that in middle-age supernova remnant, so something that is 10,000 years old, we have evidence that there are protons that are accelerated there. So we have evidence that electrons are accelerated, and we have also evidence that protons or hadrons are accelerated there. The problem is that also when you have hadrons accelerated there, they don't extend up to the PeV. And in the P-win, we don't have evidence, and there is no clear picture yet whether nucleus can be accelerated from the pulsar surface. There are some theories, but we don't have any other clues. So that's why I was saying at the end that P-wins could be electron pevatrons, but not yet proton pevatrons, and this is the missing part.
I'm not sure, because many people have...
Use the microphone.
Yeah, many people are claiming that that have observed in different sources. Maybe they don't know exactly how they are produced, but that very high energy PV gamma rays comes from hadronic reactions.
Yeah, I know it's a discussion in the field, and one thing that is not clear in the field, for example, is what is a pivatron? So somebody claimed this with a different definition than other. For example, it's not because you see a photon at 100 TeV that your source is necessarily a pivatron. What we need is that the spectral index doesn't break up to PeV. So if you have a source that is curved like that, so the break is here, but it's very bright, then you will see something here, but you are in the tail of the break. So that doesn't, your source was breaking before. What we want is a source that is this and not this. But then that's a question of nomenclature and definition. Some people call pevatrons different ways.
Yes, Johan.
Merci pour la présentation. I have a question on the deficit of PeV that you showed in the remnant. Will it be, in principle, the spectrum is the result of in situ acceleration modulated by diffusion, transport of cosmic ray outside of the shell? Will it be that just the diffusion model at those energy completely fail, and just the diffusion above a given momentum energy is stronger than what we think it should be?
Well, what we measure in gamma rays is the in situ spectrum. So what you get from gamma ray, TeV and GeV is those cosmic rays, accelerated particles, interacting locally with density, and you observe them locally. So those ones have not been transported yet. Then what we observe at Earth of the cosmic ray spectrum, this one has been transported. And so maybe the energy break of the PeV that we observe, the modeling transport in the galaxy is not accurate, but I'm not sure that there is enough parameter space to compensate. But really what we measure in camera is the in situ ones, so they have not been transported yet.
Can I ask, can you go back to the slide that you had just before moving to CTA, and elaborate on your claim that I'm not sure I understood the correlation between the morphology and the issue of whether you accelerate protons or electrons? Are you saying that a different morphology at different energies would tell you that there are different channels?
So maybe the idea is the following one, is that if you have a remnant here, always the issue is that in order to accelerate at high energy, you need a high shock speed. But a high shock speed could only exist if the density is low. If you have a wall of density, the shock will stop. And so that's this correlation here. And so what you could have is that if there is a dense cloud here, the shock here will be slower, but there will be a lot of targets. So this will produce a lot of gamma rays. And this will dominate your source if it is not resolved. But you could have also some particles that are here. There is smaller density, so there will be smaller gamma rays, but those one could be the pevatrons. But the problem is that you are dominated by the flux of this because there is higher target density. And if you cannot resolve the source, then this is just 1 point. If you could resolve spatially and make the spectrum from one region that is faint, so you need better PSF and higher sensitivity, and make the spectrum from this part, then maybe you will see that when you have a dense cloud, you have lots of gamma rays, but with a spectral break, because the shock here has been decelerated by the cloud. And in this region, lower density, higher shock speed, less gamma rays, but harder gamma rays.
I see, but it's not correlated to it's not related to the issue whether those are electrons or ions producing the.
Yeah.
Okay.
But if you can resolve the source, then different regions have different acceleration condition. And the problem is that this is probably fainter. The thing that we want is probably fainter than this other one. And so when you don't resolve the source, you're dominated by the one that emits the most.
But you do already resolve some sources, for instance, 1006.
But 1006 is, so yeah, in some cases, you resolve the location one, but you don't have enough sensitivity to make a spectrum here, here, and here, and here. But some of them, in some cases, we can, and the conclusion is that everything is electron.
Okay, so this is both what CTI will bring, the sensitivity and the resolution.
Yeah.
Okay. Other questions? Yes, please.
Me? Thank you for the talk. Naive question. So if you use a microcalorimeter, right, you gain a lot of resolution in energy, if I understand well. But what about the spatial resolution? Like how does it work? Do you lose something like that?
Yeah, so those are, from a distance, those are two different things. But when you look at the hardware, they are somehow anti-correlated. So the PSF for your instrument is mostly the mirror. How good, how polished is your mirror? Then, so some have been made that have incredible. Chandra has 1 arc-second resolution, and Athena will have 6, 7. So it will be not as good as Chandra. But the thing is that if you have lots of small beams, you need a big mirror to have plenty of photons to fill in those beams. And so if you need a big mirror, it's complicated to do a well-polished, very big mirror. Either you make a small mirror and you polish it very well. If you make a big one, then it's not impossible, but it's very expensive. And the other thing is that in your detector, Chandra has, I don't know, 50,000 pixels. On a CCD, it's easier to make small pixels. In here, the pixel cannot be too small because you need to read the temperature difference, multiplex this, and it's a new technology. And so in the end, we have less pixels with bigger pixel. So the PSF is not as good because you need a bigger mirror and it's expensive and the pixel size is bigger. So in the end, you have less pixels. And so in the end, we will have, it's not a direct cause, but we will have a slightly slower, but better than XMM, but not as good as Chandra.
Yeah, thank you for your talk. So as I understand, you have talked about young supernova remnants, right?
Yeah.
So I was wondering out to which kind of maximum distance you can still detect your supernova remnants.
Good question. So yeah, that depends on the brightness and on the wavelength. For example, in the LMC, we see 87A, that is a young 35 years old supernova remnant. We have a large collection, maybe 50 supernova remnant in the LMC and SMC. And we also see in a radio, you can see, or in optical, you can see some remnants in nearby galaxies, M31, for example. But then the further the distance, the more they are polluted by the environment, and it's difficult to make the separation, etc. But
yeah, sorry, I wasn't clear in my question. I meant like the distance from the explosion. Yeah.
The distance from
the explosion of the object, like the maximum distance of the ejecta.
Before they are no longer a supernova remnant, you mean?
Yeah.
So yeah, what will happen is that with time, they will mix, so the shock will slow down. At some point, they will almost not move, and they will dissolve into the ISM. And the ones that I show here, the smallest one was maybe 3 parsec. The largest one was maybe 20 parsecs. Mm-hmm. And typically, I don't know, maybe after 50 parsecs, the shock has slowed down. But then it depends on the environment. If you have a really dense environment, this will happen faster, etc. But yeah, let's say 50 parsec at that point, they are completely mixed into the ISM.
Thanks.
Okay, well, I see no further questions. So let us thank Fabio again. Thank you very much.
Thank you.